start the first seminar in this program by Jan van Neerven from the Netherlands, Delft, and he will speak about what he will write on the blackboard.
Domain identification.
Okay, domain identification. Our pleasure.
Jesus, thank you very much. This talk will be a bit of an improvised nature in the sense that I got a late notice that it's preferable to have the talk today rather than tomorrow, and I was actually planning to prepare the talk this evening. So let's just see how things go. Let me first mention that this is joint work with Jan Maas, who was my PhD student, who's now in Bonn. And the talk is based on two papers of ours. One has already appeared in JFA last year, and one is on the archive. I'll give you the coordinates. That's it. So now I could start this talk in various ways actually. It is on the intersection of various fields of activity. I could deliver this talk to SPDE people, but I could also deliver it to people coming from harmonic analysis. Actually what we're solving is a problem that is that has its origins, as far as I'm concerned, in stochastic analysis. However, the methods, and that will become clear in my talk, are largely influenced and motivated by recent developments in harmonic analysis, and to be specific, by the recent solution of the Kato problem in harmonic analysis. The Kato problem is a problem about identifying the L2 domain of a divergence form elliptic operator with bounded measurable coefficients. So it's conjectured by Kato that the domain of the square root of this operator, so you look at the form and then you define the divergence form operator with it. The Kato conjecture is that the square root is the first Sobolev space. Now, for second order operators, this has been proved correct by McIntosh and a number of his collaborators. And fairly recently, a new proof was given by, of the Kato conjecture was given by Axelson, I think it's double S, Keith and McIntosh in Invenciones, where the basic idea is to reformulate the problem about these second order operators into a problem about first order operators. And this turned out to be an extraordinarily useful idea also in the analysis of the problem that I'm concerned with. And good fortune has it that when at the time I was struggling with this problem, I was visiting Alan McIntosh in Canberra, and he explained me about his paper. And it gradually started occurring that his methods could actually be used here. These harmonic analysis methods are based on harmonic analysis in domains on RD with Lebesgue measure. I'm, on the other hand, will be concerned with Gaussian analysis on a Banach space with a Gaussian measure. So that makes the analysis rather different from a technical point of view. Some parts in the analysis in the Kato square root problem, which are easy, are actually the hard parts in this analysis, and vice versa. And if you make the comparison, you could say that what I'm doing here is an infinite dimensional version of the Kato square root problem, but for constant coefficient second order operators, but in divergence form in a certain sense that will become clear. Whereas, of course, the whole deal about the Kato square root problem is to have bounded measurable coefficients, the constant coefficients case being largely trivial as far as the Euclidean case is concerned. Okay, so that's about the introduction. So let's now start. So I'll start my talk from the point of view of SPDE and write down the equation that's so simple that I feel embarrassed to do this here. But here we go. So the underlying stochastic equation is plus some initial condition, let's say. So what's the setting? The setting is WH is a cylindrical Brownian motion over some Hilbert space H. So formally you think about WH as, so you specify an orthonormal base in the Hilbert space. You run in each direction of the orthonormal basis an independent one-dimensional Brownian motion, and you add things up. That sum will of course diverge, but there are ways to make this idea rigorous. For instance, in Maillard-Vin calculus, this would be an example of an isonormal process. The correspondence being that the Hilbert space for which this is an isonormal process would be L2 in time with values in this Hilbert space H. All right, so that's W. My process lives in a Banach space E. And the operator A is the generator of a strongly continuous semigroup on E. And for the purpose of this talk, actually, it will be convenient. I'll be talking mostly about analytic semigroups to add a minus here and a minus here. That avoids a lot of minuses later on, because basically I'm going to consider the operator minus A and its properties.
So is there any relation between E and H?
Yes, so that's the next point. So for simplicity reasons, but that's not essential, I will assume that, that H is embedded in E. By means of a continuous injective embedding. However, this is just to make the formulas look a little simpler. This could be replaced by any bounded linear operator mapping B into H. So you think of H as something that comes from the noise, and then B would be some operator that transfers this noise into the state space E. And for simplicity, I assume this to be an embedding. And let's call the embedding operator I.
So in the same spirit question, you cannot, even if you assume that A is a generator of minus A of analytic semigroup, you cannot take H bigger than E.
H comes from the noise.
So if you take H equal L2.
Yeah, but that's about specific applications.
No,
so,
yeah,
so
but
yes.
it's specific. But I'm asking whether your results you don't have to speak about.
Oh yeah. So in an example, typically, my Banach space would be LP on some domain in RD. H would be L2 of D, and now you see that you already have a problem at this stage for, say, for one half of the piece. If P is between 1 and 2, of course, you have this embedding. However, to apply the ideas of this talk to, say, the stochastic heat equation for LP with P bigger than 2, you would typically take some negative extrapolation space for a suitable power where alpha is taken so large that L2 embeds into the negative Sobolev space.
Yeah, I understand that you can do it, but in a sense, the space LP with P bigger than 2 is natural space for solutions in this equation.
Yeah, but then the regularizing effect of the semigroup comes in, and it maps you back, say, into an interpolation space of this one. But regularizing effect is bigger than the alpha you need to take here, so you end up being back in LP with your solutions. So that's typically what happens in this kind of applications. However, what I'm concerned with here is just this simple setting, but it could be applied here with ad hoc arguments.
We're using with ad hoc argument, okay.
Well, the ad hoc argument being that you don't take E as you think you would, but you would take E to be this negative extrapolation space. So this would be in the range where P is bigger than 2. You could take, of course, LP itself in the range
And you,
below 2.
my question was really whether you formulated results in this way, that you apply them to the spaces, or you just think that they can be formulated.
This is just an abstract talk, so there will be abstract objects and an abstract
Yeah,
theorem.
I understand. Okay, let's continue, because then we never finish. And
The theorem would by no means be easier. Well, no, there's not entire. Yes, none of the results would simplify if I would just keep in mind the simplest case where E is just L2 on the domain. Okay, so if you dislike the idea that H is bigger than LP for one side of P, well, just keep in mind that the simplest case P equal 2.
okay.
And for the analysis that I'm going to do and for the results I'm presenting, that's already equally hard as a general case. Okay? So, okay, so we have this setting, and now we make another assumption. We assume that this problem has a weak, which is the same as a mild, because we have additive noise solution. And not only this, we also assume it has an invariant measure.
Give some simple sufficient conditions.
Yes. So in the case of a Hilbert space, you know that you do have solutions. For instance, if this inclusion is Hilbert-Schmidt, and in general you get conditions replacing this. So you can actually relax this assumption about Hilbert-Schmidt in the Hilbert space case a little bit by saying that certain operators should be of trace class type, and in the Banach space case it has to be replaced by certain operators be redonifying. I don't really want to go into this, but I just give some examples where all this is satisfied. If the space has type 2, so for instance, E could be an LP space for P in the range above 2. And this inclusion is redonifying. That would be just a direct generalization to the Banach space context of what you mean by saying that a Hilbert space map is Hilbert-Schmidt. Okay, so
this for my solution of what you need to have a variant measure.
I'll come to that in a moment. So this is about existence. And the second example is not a condition on the Banach space, but on the semigroup. S is analytic. And again, I is redonifying. Well, further examples can be given where I is not redonifying, but nevertheless solutions exist. So then basically the redonification, so the Hilbert-Schmidt condition in the Hilbert space language comes from the semigroup. And the sufficient condition for the existence of an invariant measure in each of the two cases. So in these examples, a sufficient condition for the existence of an invariant measure is that the semigroup is uniformly stable for invariant measure. Is that semigroup has some negative exponential bound, so for some constants m and omega. Right, because then basically what you can do is you can write down the covariance operator of what should be the invariant measure, and that becomes a convergent integral because of the decay of the semigroup. However, I should point out that there are some strange things going on here. First of all, examples can be given even in the situation where W is a one-dimensional Brownian motion in the Banach space and where the semigroup is strongly continuous, where you don't have existence of weak or mild solutions. And that's because certain stochastic integrals fail to exist. This is in sharp contrast to what you have in the Hilbert space case, but in the Banach space case this happens. And examples where that happens typically live in the range LP for P below 2. So this is the bad part of the LP range, because you fail type 2 in that case. And the semigroups that do it are, for instance, rotation semigroups on the circle. It's a simple computation based on the Kahane-Kinch inequalities that you can characterize when, for translations or rotations on the circle, your stochastic integrals exist, because you can compute them explicitly using Kahane inequalities. And you find you can actually characterize the directions in your LP space where the Brownian motion is allowed to live if you want to pick up solutions. So the result is for this example that if your semigroup is rotation on the circle and your Brownian motion is in the direction of a certain given element of LP, then a weak solution exists if and only if that direction is in the direction of an L2 vector.
Is it true that if the mass relation exists, is given by the natural stochastic integrals?
Exactly. Yeah. So the solution is given by the semigroup acting on the initial value. So S of t denotes the semigroup generated by the generator, and then the stochastic convolution of the semigroup with this cylindrical Brownian motion. And of course, one has to make this thing rigorous, but to make this integral rigorous, you say a function has a stochastic integral, so stochastically integrable, if there exists a e-valued random variable such that if I apply functionals from the dual space, it should give me the random variable applied to the functional, right? So that's
not essential, but your initial condition is 0.
Oh, that's sorry. I want to consider.
0.
Sorry.
X of t is it?
X of 0. X of 0.
Okay, sorry. Of course.
Does your invariant measure live on H?
No, on E.
On E?
Okay, so the invariant measure would be limiting the.
Windows
So this is E valued. So it has a distribution. Let's call it mu t, which is a centered Gaussian measure. Solution is an E.
Have a smoothing effect, okay?
If I try to be entirely precise, I should write this inclusion here. So there's this noise, the inclusion includes it into E, and then the semigroup takes over, which sits in E, and the stochastic integral that comes out is E valued.
No, I don't mean the stochastic integral. I meant the.
Yes, but the semigroup is E valued.
I'm talking about the invariant measure.
Yeah, but that will be a limiting distribution, so it will be, basically it will be the weak limit.
So you don't have any
Of these
regularizing
measures.
effect.
Sorry?
There's no regularizing effect.
The measure could actually be very smooth and live on better subspaces, but a priori all you know is that it lives on E, and it is a centered Gaussian measure on E. And the covariance,
But probably most cases it would be an H.
I will need this anyway, so let's be precise. This covariance is given by a bounded linear operator which now acts from E star into E. In the Hilbert space case, you just have bounded operators on your Hilbert space. You use the self-duality of the Hilbert space. In the Banach space case, these become operators from the dual into E. And explicitly, this is given, as you would expect, it is the integral of the semigroup, and then I star, and then the adjoint semigroup, ds in the strong sense. Or dt.
Can you include the case C is, for example, is a continuous function? The
Banach space. Yes, except that in that particular case, it will be very difficult to check these redonification conditions, which give you the example. We can give necessary and sufficient conditions for the existence of weak solutions in terms of certain operators being redonifying. And those assumptions are fulfilled in these two cases. So these are the easy cases where this can be checked by abstract arguments. However, if your space is continuous functions, the theorem applies,
right, okay.
but you would have to prove redonification in the continuous function, which is hard.
But But the continuous function is not type 2, right?
No, exactly. So this example doesn't apply. But the general theory does apply. The general theory is just for general Banach spaces as long as additive noise is concerned. We have papers about multiplicative noise. So there your stochastic integrals will not be deterministic in terms of the integrand, but you have to integrate processes. And well, and then there are various approaches. So there's the M-type 2 approach. We have developed a UMD space approach, but you need some properties on your Banach space to make things work. Okay, and then the continuous functions would be excluded. But for this very simple setting, you can do it in complete generality. Okay, so we assume there's this invariant measure, and if it exists, it's unique, and the covariance is given by this formula. And for this, I refer, at least say, the formulas are all there, except that here we have dressed it up a little more general to Banach spaces, but this is all in the Prato-Zapsik book. The red book. Okay, so this is the setting, and once we have this invariant measure, we can ask about strong continuity of transition semigroup. So now on the space of bound continuous functions, define. So let f be a function from this space. We define, as usual, for x in E, we define this to be the expected value of, so you run the function over the solution, I use letter capital X, with initial value x. So xt of x means that x is the initial value of my problem. And so this defines again a bounded continuous function. However, because we're working with the soup norm in this space, this typically tends to be not strongly continuous. It is pointwise continuous in x, locally uniformly both in time and in space. So it's uniformly, it is uniformly continuous in time on compact subsets of x, but that's all you can say in general. However, due to the presence of an invariant measure, we can extend this semigroup. So there's a unique extension of this semigroup to each of the LP spaces over the invariant measure. Right? The bound continuous functions are embedded in each of these LP spaces. And it turns out that the action of the semigroup is strongly continuous in the LP norm. And that's just an application of Jensen's inequality. So this semigroup has a generator. So let minus L be the generator.
Did you mention it is strongly continuous?
No, it's not.
Oh, sorry, strongly continuous, of course. That's the important point here. I think I said it in words. And because it's strongly continuous, there's an unambiguous definition of the generator. And now the question is, so that's really what the talk is about, what's the domain of this operator? Now to get a first idea, let's have a look at the explicit expression for L. So it can be shown that, say, on a suitable core, we have the following expression for L, for minus L. So if f is a simple enough function, so for those who know about it, it should be a cylindrical function, which is twice differentiable and bounded, with bounded derivatives up to second order. So that would be a core for this generator. So it is dense in the graph norm for the domain of L. And for such functions f, we have the following pointwise expression for the generator. It is 1/2 times the derivative in the direction of h. I will come to that in a moment, what I really mean by this, squared, and then the trace. And because minus a is my generator, there will be a minus here, but that's because the convention on signs. And now I have a reason for putting the a on the other side that will become apparent in a moment. Like this. So this is the Fréchet derivative. And this is the derivative, well, basically it's the Frechet derivative in the direction of h.
We mean Gatot,
Sorry?
which is Gatot derivative.
Direction. Yeah.
No, it's not a direction derivative. It's really a global object. Oh, I'll write down the formula in a moment.
But
It is something like the Maillard-Van derivative of Maillard-Van calculus, except that I'm not differentiating in the direction of the reproducing kernel space of the invariant measure, but which is another Hilbert space which is embedded in E, but I'm taking A, H, the one from the noise, but then formally take the same approach like you would do by defining the Maillard-Van derivative, so D of H. So because this is a Frechet derivative, this will be E star valued. So A star will then act on the values of this expression and will give you elements in the dual, and they act on X by duality. Okay, so that's how this is interpreted. Well, and here you differentiate in the direction of H, so that will be H valued. So if you do it twice, you end up in the tensor product H tensor H. Then you take the trace, which is then well defined, and 1/2 of that. Okay.
so what you really consider is you mean that the dH is a linear operator from H to H?
Yeah, dH.
dH, yes.
No. dH lives in, say, in LP of E with respect to the invariant measure. So I'll come to these formulas now. So here, so for a function which has this form, so I take cylindrical functions, and by that I mean that there exists a real valued function in n variables, such that fx takes this form for a suitable choice of functionals x1 up to xn. So if your function f is of this form, it's called a cylindrical function. And if phi happens to be from CB2, so twice differentiable with bounded derivatives, I'll say that this is a cylindrical function that's twice boundedly differentiable. So for such functions, this is pointwise correct.
The coupling is in A.
Sorry?
So the coupling in the T is in E.
Between
So phi lives on Rn.
No, I mean so the coupling in product is on A or coupling between.
Oh no. So this is for x and E, and the functionals in the dual. So this is the duality between E and its dual. And so now the derivatives are given are defined actually by the following expression. So you take partial derivatives of the phi. So the partial derivative in the j direction in Rn, of this whole expression times xn star. So that's how it becomes E star valued. And similarly, the derivative in the direction of h is given almost by the same expression. But now you apply to the Frechet derivative, you apply the dual embedding. Remember that I maps H into E, so dually we get a mapping, well actually a bounded linear operator, well into H star, but I will identify H star with H. So that will be, this will be I star. So I star can be applied to functionals, and if you do it, you end up with elements in your Hilbert space. So as I mentioned, this is not the Maillard-Van derivative in the direction of the invariant measure, but I will need that object anyway. So let's agree that I call H infinity the reproducing kernel Hilbert space of the invariant measure mu. So
I don't understand one thing, because when you said Frechet derivative, but and then you said presented this as a definition. But if you use the definition of a Frechet derivative, this is an access.
You're right. You're right. Okay. So indeed, you're right. So the Frechet derivative can be defined in its own right. And for cylindrical functions of this forms, it takes this simple form. And similarly, you can define in abstract terms a Frechet derivative in the direction of an embedded Hilbert or Banach subspace. And then for these simple cylindrical functions, like this, this object here, it will take this form. But alternatively, you could take this as a definition and then look for closability properties of such derivatives.
Yeah, my question was,
So
what is it?
I agree. You're more precise than I am. So
No, I'm not
if you
more
like,
precise.
take this as a definition, and
Yeah.
then we worry about.
No, I understand.
Okay, so
But this is a Frechet derivative.
it is a
This is
Frechet
the
derivative.
case.
Yes.
That's what you
yes,
said,
yes. In the direction of this embedded space. But the way I think about it is really by these formulas, because all the computations later in the proofs will actually be just on cylindrical functions and then use density arguments to lift things right. And also these expressions, they fail to make sense unless the function is cylindrical. They fail to make sense in a pointwise sense. Okay.
So what is the status of cylindrical functions in O? Are they weakly dense in the whole?
They are dense in LP on the invariant measure for every
Weakly-
choice of P. No, strongly.
Strongly dense.
Strongly dense, yes. Okay, so
This xi star must be in the domain of A star, right? You want to.
yes, formally yes. So okay. When I say that this makes sense on a suitable core, the core is really
Can you write down a core, please?
yeah. So this core is the cylindrical function. So you typically that people write it like this. So the F stands for cylindrical. I don't know where the F comes from because a C would make more sense, but people write this on E. But now I put a comma, and now to give a meaning to this expression, indeed I do need that the functionals that come out if I do the differentiation should be in the domain of A star. So that's why I write domain of A star. And more generally, of course, you could define such space of cylindrical functions by putting here any embedded Hilbert space or subspace of the dual space. And you can prove that this is still a core for the operator L.
Really a core.
It is a core. This space is dense with respect to the graph norm of the domain of L, when L is the realization of this operator in, so L is a generator in this
LP.
LP up there, yeah. It requires some effort, of course, but this can be proved. In fact, it doesn't require so much effort. It is dense in LP, and it is invariant under the semigroup P of T. And if you have a dense subspace which is contained in the domain and it is invariant, then you know it's a core. Okay, so that's basically how the proof goes. Okay, so I'll also need this embedded Hilbert space H infinity, which is defined to be the reproducing kernel space of the invariant measure. So that's the space that's embedded in E by means of another embedding which I denote I infinity. So dually we have an I infinity star which maps E star back into H infinity. Well, it need not be an embedding, but it's at least bounded. H. And now what we can do is look at really at the Neerven derivative. Which I will denote dH infinity. And that's again for cylindrical functions defined by in a point x by the same expression, partial derivatives of these inner products. But now you take this dual mapping to make sure you end up in H infinity. So you have three objects. So you have some obvious identities here. You have, I'll need them in the following form. You have that the Neerven derivative could be written as this dual embedding composed with the Frechet derivative. That's obvious, right? Because it's just plugging in this extra operator. And now I'm going to do something very scary. I'm going to write d of h as some operator composed with D. Now what is V? V is the following operator which has as its domain, as its initial domain, the range of I infinity star. So it is an operator which maps I infinity star x star to the vector I star x star, which is the guy that appears here. So with this operator, it's clear that if I apply V to this dual embedding, I'll pick up the other dual embedding, and I get that expression. However, there's a point here, because I'm not assuming that the invariant measure is non-degenerate. I have no information about whether the dual mapping is injective. Right? That's equivalent by Hambana. So I'm allowing a degenerate invariant measure. So I'm allowing this map to be non-injective, and therefore there's a well-defined expression here.
Could you explain what it means when you say degenerate? What does that mean?
Oh, I just mean that there is a proper closed invariant subspace which has measure 1 for this measure mu infinity. Okay, so the actual support in the topological sense of the measure is a smaller closed subspace. So I'm allowing that. But nevertheless, it turns out that, say, on the very mild assumptions, this is a well-defined mapping, and in particular in the setting I'm going to consider in a moment, this turns out to be well-defined. However, the initial domain being just this range has no good reason why this should be any good operator. So now there's the following question arising. These elements are they form a dense linear subspace of H infinity. So they are dense in H infinity. And these functions, so if X star ranges over the whole dual space, then this is dense in H. Okay, so I get a densely defined linear mapping. But now the question is it closable? Okay, so this question can be answered. Let's see, I think I take this blackboard. So examples can be given in the present setting where this fails to be closable. And this can again happen even in the case when the original noise, so the W, is one-dimensional. However, there are various sufficient conditions for this mapping to be closable.
Just one simple question,
yes.
Jan. Namely, you wrote that dH infinity is equal I infinity star composed with D.
Yes.
Because you can just apply I infinity star by linearity. And
Yes.
why you cannot do the same with I star?
Yes, definitely. So this would be oh, sorry. This was missing, and it will be I star composed with D. I'm sorry for that. But I won't need this. It's true, but I won't need it. In fact, I will hardly need this. But this is the important one. So this operator V. All I'm trying to say is that this operator V pops up in a rather natural way. And
what the difficulty was.
The reason, before I turn to sufficient conditions, let me state an equivalence. So the following are equivalent. So the operator V as a densely defined operator from H infinity to H is closable as a densely defined. So on this initial domain, it's well defined, but you ask, is it closable? It is closable if and only if this derivative dH is closable in as an operator, so as a densely defined operator from well, it lives on LP, but the values are H valued. So it maps into the h-valued function sitting on E. For some p, and once you have it for some p, you get it for all p in this range. Okay, so this is the reason why the operator V is important. It gives you a way of testing closability of this gradient, which plays such a prominent role in the definition, or actually in the representation of the operator L. So the gradient in the direction of h comes in naturally here. It is basically the Laplacian which is responsible for the diffusion part of this operator. So you think of this as an operator having a diffusion and a drift part. So A stands for the drift, and this stands for the Laplacian in this infinite dimensional sense. And because the noise is modeled on the Hilbert space H, this Laplacian will be the H Laplacian, in the sense that it is the square of this gradient. And now you will have no results whatsoever of any use unless dH is closable. And now this result gives you the criteria for closability. It tells you that in order to study this operator in the LP setting, it is sufficient to go back to the Hilbert space situation and look at the operator V. Right? Because this is just the operator between Hilbert spaces, density defined, very explicit. And your question is going to be, when is V closable? And then you solve this. And the moral reason for this is that these objects H infinity and LP over mu infinity are related by second quantization. I don't want to really go into this, but the idea is that there's a sort of functorial way to build up L2 over the invariant measure from H infinity basically by using generalized Hermite polynomials. Right, so I think everybody knows basically, and then the summands are the chaoses. And this procedure is called second quantization. And in a way that can be made precise, you have that the second quantization of this operator V is dH. So I put it in parentheses because one has to make this rigorous, but this is going to be a sort of leading idea in everything I have to say. So it enables you to transfer Hilbert space results up to the level of LP on the invariant measure in a sort of functorial way.
But this your H infinity must be very closely related to H under this condition.
Yeah.
Do you have a concrete condition, not just a closed spot for if and only for another closed spot?
In certain examples,
yeah,
it happens by a stroke of good luck that H infinity is embedded in H.
okay.
But in general, there's not much you can say.
Yeah,
and if you have H infinity embedded in H, that is basically equivalent to the operator L having a spectral gap. That's the kind of results you can prove. But in general, it's hard to say anything reasonable. So what I would like to do now is dwell a little further on this and now go into the problem of determining the domain. Now, what we really want this operator L is to be really something like an elliptic operator. So what we would like is that this semigroup P of T is not just a semigroup, but it should be an analytic semigroup. Right? The intuition being that this is basically a second order operator with a first order drift term. So morally speaking, this semigroup P should be analytic. So let's have a look at when this happens. Perhaps I should say that this is a result due to Ben Goldis, Fausto Gozzi, and myself in potential analysis a couple of years ago. It's not so hard, and we used it to analyze some concrete examples. The next result, this also has a long history, but in the form stated, it comes from a joint paper of mine with Ben Goldis. But many people contributed this, so prior to this there were results by Goldis, Fuhrmann, and many others. And it gives necessary and sufficient conditions for the semigroup P of T to be analytic. So in this framework, the following are equivalent. One, the semigroup P of T is analytic on on LP for some P. But now P has to be in the reflexive range. Second, the same, but for all P in the reflexive range. And the third is, I should make a preliminary remark, and I should have made that at the moment I introduced this reproducing kernel space H infinity. It is an older result of Choinovska-Michalik. And Goldie's. That the following happens. Well, we have this space E, and in there is this subspace H infinity. And now by some miracle, it happens that the semigroup acts in E. But by some miracle, it happens that this space is always invariant under the action of the semigroup. Right? So we have the situation that S of t restricts to in effect, to a strongly continuous C0 contraction semigroup on this space. So let's denote this restricted semigroup by S infinity of t. And let's denote the generator of this semigroup by minus A infinity.
So this is an assumption.
This is the theorem, and it always holds, and there's no analyticity needed for that. So this is a general fact. As soon as you have an invariant measure in this simple setting of a linear equation with additive noise, as soon as you have this H infinity, the semigroup will leave it invariant. And the proof is an exercise in the Riesz representation theorem. It's fairly easy. The starting point is, of course, this formula for the covariance of the invariant measure, and then you look what happens if you add a semigroup operator to that and analyze this, and then you find that this works. So it's not hard, but it's a very nice and very important observation. So now the statement here is that this semigroup is analytic on H infinity. The reason is, again, so this is another result by Choinovska-Michalik, at least in the Hilbert space setting, but it is equally true in this Banach space setting, that the underlying reason here is that if you quantize this semigroup adjoint, it turns out you pick up this P of t. Right? So analyticity of this semigroup translates via second quantization to analyticity of this semigroup. And in the converse direction, if you are analytic on L2, then by restricting to the first Wiener chaos, you recover this semigroup, which is then analytic, and then by duality, this one is analytic. So this is easy to understand why it happens if you know that this is true. Okay, well, and for those who are interested in how do you check this, you check it on the exponential vectors, which are dense. And on the exponential vectors, it's a trivial computation. Okay, but now for me, the fourth important point is that the following is true. That, okay, so we have this operator Q infinity, which is the covariance operator of the invariant measure. It acts from E star, so this operator acts from E star into E. So on the right of that, I could write the operator A star. So A star acts here, and then Q infinity brings you to E. Now you could start not from a vector E star, but well, let me a little bit sloppy. So this restricts to a bounded operator in H, not H infinity. It's not so important where all this comes from and what it really means, but again, here's some simple intuition. You probably know this formula. It follows by simple algebra on the expression of Q infinity, that if you add the adjoint, which is then formally this one, you pick up, and now I use the sign convention that negative A is the generator, so this will give plus identity. Usually it's written like minus identity when A is the generator, but in our setting, minus A is the generator. And now let's call this operator B. So then this is B plus B star equal identity. And there's a dual condition that I perhaps could also write down equivalently. So this is phrased in terms of what I call here B, and then dually this has the same property. So somehow for free you get some operator sitting there on the Hilbert space, and this is not just an operator. So let's call this restriction the action of this operator in H. So maybe it's a bit mysterious how this could act in H, because there's no relation between E star and H. So what do? You take a vector of this form. Well, that definitely sits in H, right? Because I apply the adjoint embedding. And now I think of this as being mapped to Q infinity of A star of X star. So I just peel off the X star, the I star. I just take the functional where it came from. Then I apply A star, then apply this. So this ends me up in E, right? Now I could be lucky, and by some stroke of miracle, this could be not in E, but in H, which sits in E. Okay, and now here, so the interpretation of this phrase number 4 is that happens. So for every X star, it is true that this mapping is well defined to begin with. So I can take off the I star. And it ends up not in E, but in the smaller subspace H. And as such, it will extend, because this only gives you a dense subspace of H, but it boundedly extends to an operator from all of H into H. Right? So it's a bit of a subtle thing here, but it turns out to be equivalent to the analyticity of the transition semigroup. And now the interesting fact happens. So now we get into business. If this happens, so if these conditions hold, then we have the following representation for the negative generator. So minus L was the generator, so L is minus the minus L. It has this form, so call this operator B. So the realization in H I call B, and now we forget where it came from. Just important that we have this B, but now it turns out that so this is the representation of L in non-gradient form, but it turns out to be divergence form. It turns out that L has a divergence form representation. It turns out to be dH star B dH. So have a look at this. So dH maps you into the H-valued functions. Then pointwise in the range of this derivative you apply this operator B, which lives in H. And then you go back with D star. This, of course, in the L2 setting. So dH will now be the realization of this gradient in L2 of the invariant measure, and then you have, so in L2 you have this gradient form, and I see that I'm again ahead of my own thoughts, because you may rightly object that D star need not be well defined because DH need not be closable. So I should have added here, so if these conditions hold, then first DH is closable, and this formula holds for p equal 2. So it's closable in any of the LPs, and well, that follows from this result, right? Once you have closability in 1p, it's for OP. So it's closable in particular in L2, and then this formula makes sense and gives you an alternative description of L in divergence form. Right? So if you think of this as a gradient, you think of this as a divergence. Okay, now the main results. Let's see, time is going rapidly. Oh, my watch stopped. No wonder. That's what. Oh, time is going rapidly. I've been asking too many questions.
You'll have to recycle your battery.
Yeah. No, this is windable. So here are the two main theorems. Well, actually, the second is the main theorem, but to understand the second, I first need to give the first theorem. Okay, so we have seen that this space H infinity is always invariant. Now you may ask, how about the space H? Now, a moment of reflection tells you that, of course, that will not, in general, will not be invariant. And why should it? Because if you go back to the original data, what are the data? The data was just a semigroup and some cylindrical noise which is embedded. But there's a priori, of course, no relation between the objects, and there shouldn't be any in general. That this guy here happens to be invariant is because it refers to the invariant measure, and in the definition of the invariant measure there's implicit both the actions of the noise and the semigroup. So this has a chance to be true, and it is in fact true, but the original space H need not be invariant. Now the amazing thing, I still think this is an amazing result, and Ben Goldis and I have tried for years to prove it, unsuccessfully so, until I was in Canberra, and McIntosh was showing me his work with Axel and Keith, and they actually had results that showed us how to do it. So the result is that if the transition semigroup is if the transition semigroup is analytic, so I'll just use this phrase just to abbreviate the statement that we are in the equivalent conditions of the theorem. So a necessary condition for analyticity is that H is invariant under S of t, and moreover, the restriction to this space H is a strongly continuous, analytic, uniformly bounded semigroup. And by uniformly bounded, yes, uniformly bounded on some sector. And so there's always a bit confusion about what you mean if you say analytic semigroup is bounded, because you could mean that it is bound on the real axis and has an analytic extension to a sector, or you could mean that on the sector it's bounded. So I mean here bounded in the strong sense, it's bounded on the sector. Okay, so that's the first statement. And the second statement, so this is in our paper with Jan Maas, but in all the results, so we were studying this with Ben Goldis, and we could prove a sort of converse that you have the following. If the semigroup restricted to H, well, and now so if S restricts to a semigroup on H, so if S leaves H invariant, and the restriction is an analytic contraction, so a C0 contraction semigroup, it's even enough to have that in some equivalent Hilbert norm of H. But this is sort of trivial side remark, because I never said what the topology on H is, so I could change the topology on H for free and do the same framework. So if this is contractive, then P of t is analytic. So you see there's a very tiny and subtle gap between the equivalence of these statements, and the gap sits exactly between contractivity and boundedness. This looks like a minor little thing, but it is actually crucial. There are examples of uniformly bounded Hilbert space semigroups which fail to be contractive in any equivalent Hilbert space norm. Of course, you can always make a semigroup contractive in a trivial way but that gives you a Banach space norm on the Hilbert space for which you get contractivity. And such norms typically do not come from an inner product. So here we insist on having an equivalent inner product generating an equivalent norm. And then boundedness cannot be reduced to contractivity in general. So why is this so important? So now we come to the main result of my talk. So the question was about this domain of the operator. And now remember that this minus L was roughly speaking 1/2 of the trace of the A square plus minus A of the Fauchet derivative. So what you expect is that the domain of L should be something like a second order Sobolev space of dH. But this should also be meaningful, and it should be in this first order space. And then typically you would expect to have this intersection of domains, and then hope that that's a domain. Okay? So this is informally, because I don't worry about how to make sense of this. Okay, so now the rigorous result is as follows. So let P be any number in the reflexive range. Then the following are equivalent. First. And now the idea is this. So this is really harmonic analysis. To understand such domain identification questions for second order operators, what you typically do is first you look at the square root. And usually the square root of such an operator is much better than the operator itself. And typically what you have, say, if you look just in harmonic analysis book for domains of square roots of elliptic operators, you will typically just have the first Sobolev space. Okay, so reasonably speaking, that should come out. And now if you look at the domain, if you look at the representation, you see that roughly speaking, one inclusion should be true simply because of this divergence form representation. But then B comes in, and B just mixes up things, and then D star comes in. So the square root is not just D of H, of course, right? So these are really profoundly different operators. But the result is this. So let me denote the LP domain by putting a P. So here I mean the domain of the realization of the operator in LP on the invariant measure of the square root of L is the domain of DH with equivalent norms, with equivalent homogeneous norms, by which I mean that in fact the following semi-norms are equivalent. So I want for functions in this common domain, I want DH f in the P norm up to a constant be comparable to square root of L of f. So there should be two-sided estimate with constants independent of f. And that's because of homogeneity, because I'm only looking at these parts and not at the norm of f itself. Secondly, the domain of, let's give this a name. So let's call this restriction, let's call that, let's call it S of H, and let's the generator be minus A of H, just to put names. Then it turns out the domain of this operator here, the square root of H, so this operator we now know to exist under this analyticity conditions. I forgot to mention one thing. I'm assuming, of course, analyticity. So we are in this framework where we do have this divergence form representation. So that's the good case because L is an analytic, is something like an elliptic operator. So this is the case where things go as we think they would go. Then we have that this is the domain of this operator V, of which we know it's closable, with equivalent norms. So now meaning that V of a Hilbert space element in the Hilbert space should be comparable to square root A of F in the Hilbert space norm. A third, and now of course the real test comes. Now what's the third condition? This is that the semigroup generated, so the semigroup S of H, we know it to be bounded analytic. It should be contractive analytic. It's contractive with regard to some equivalent Hilbert space norm. And then if these conditions hold, we can also say what the domain of the operator L is. So it requires additional effort, but it can be done. And then there's a little surprise. It turns out to be this, basically the second order Sobolev space, intersected with the first order space. But now something funny happens, and once you start understanding how these things work, it is natural that this happens. My point is that we started from a semigroup on the Banach space E, but you may have noticed that the Banach space E is totally out of the picture already for 3/4 of an hour. We haven't used E at all. We just have this semigroup sitting on LP on E, but then E is just a measure space. And we have this Hilbert space semigroups like S on H infinity and S on H. So these are the intrinsic objects, and E is irrelevant. And now E suddenly figures in this first guess by means of the operator A, which lives in the Banach space E. So we should try to eliminate this operator and replace it by one of these operators that are more intrinsic. And it turns out that the correct choice is that one needs here the domain of this A infinity composed with the Maillard-Venn derivative. That's the correct choice. And now everything is intrinsic. There's no Banach space E needed for this statement. And indeed, what we have done in our JFA paper is put up as a general framework of what one could call non-symmetric Maillard-Venn calculus, where these results are proved in a much more general setting. And I started here from the Ornstein-Uhlenbeck case just to arrive at a result that, say, originally comes from SPDE, but really what we're doing here is Maillard-Venn calculus in a non-symmetric setting. So if you allow me, I just write down some ingredients that go into the proof as a compensation for all your questions.
What the problem could be, I don't know whether the person who is recording can still continue.
Oh, I see. But okay, just informally, so how do you prove these results? So first of all, the equivalence of being contractive in an equivalent Hilbert space norm is equivalent to having a bounded H infinity calculus. This occurred already in the talk by Mark Farah, and it really means that you can give a meaning to operators of the form f of A, where f is a holomorphic function on some sector, where you need a sector with opening angle less than pi over 2. The recording device. Okay, so this is off the record. So H infinity calculus comes in, and now I mentioned that there is this first order approach due to Exelson, Keith, and McIntosh. And well, to appreciate that, you do a little computation and you check that this operator also has a gradient, sort of a divergence form. So here we had L. I should add to the list that H infinity, I should be careful, star, is V, B, dV. That's simply by second quantization what you would expect if you know that V. If you know that V quantizes to D, then this whole object V star, B. So this quantizes to this guy. And it corresponds to the idea that the quantization of this semigroup gives you this semigroup. But now, interestingly, this guy can be written with the same objects, but then as V star B. Of course, this is largely formal because you have to worry whether B maps into the domain of this unbounded operator, etc., right? But there's a rigorous way of doing this, and this suggests a new object, which I could call L tilde, which is DH star B. So the intuition, if you talk to Macintosh, says, well, this is all easy to understand. Look at this. This lives. This operator here lives not on LP, but it lives on LP with values in H. That's because I reverse the order. So you should think of brackets like standing like this. And here you should think of the brackets as standing here. And what we've done is we just swapped the two. So Macintosh would typically say, well, this is just a Laplacian, but this is the Laplacian on one forms. If this is the Laplacian, or its generalization, if this is the Laplacian on functions, then dually, so this would be the gradient of the divergence would be the Laplacian on the one forms. So there's some duality here. And now it turns out to be that we could add to the list of equivalent conditions for that. So let's replace this condition now by having H infinity calculus. So H has a bounded H infinity calculus. Then here you get that this operator should have a bounded H infinity calculus for one and then equivalently for all P. And now the fun starts, and you can start doing harmonic analysis. And the idea is now to introduce, I'm just using their notations, formally this operator matrix, where you have these two entries sitting here. Now, this is a first order operator matrix, 2 by 2. And why is this an interesting operator? If you compute the square, just do matrix multiplication, you see that here you get L, and here you get L tilde, and here you get zeros. Now, and why is this interesting? So if this is an operator having a calculus on a sector, then this first order operator should have a calculus on the bisector. Now, if you have a calculus on the bisector, it means that you can look at functions which are +1 here and -1 here, and they are analytic and bounded. So it gives you a way to encode the Hilbert transform into the bisectoriality picture. So what you are interested in the question. And now look at square root of L. That would basically be equivalent to this pi. So this is the underlying intuition now. So if you plug in vectors of the form f0, then square root of pi really reduces to these objects here. So now the objective is to prove that not just L has a bounded H infinity calculus. You see in the equivalence list the H infinity calculus here. Because L is a very good operator, you always know that this has a bounded H infinity calculus. So this follows from general principles on positive semigroups, on, say, Markovian. They have H infinity calculus. So the operator matrix has it. So this operator has also an H infinity calculus on the sector. And now the non-trivial thing is, and here R-boundedness techniques enter, so I refer to Mark Ver'aar's talk about what R-boundedness is, but under an R-boundedness assumption on the resolvent of this operator, you can show that it is equivalent to have an H infinity calculus on the sector and have an H infinity calculus for this first order operator on the bisector. So the bisector meaning this object. Now once you have this functional calculus, you can implement the Hilbert transform, and that gives you the boundedness. So what comes out of this is the boundedness of the Riesz transform of, well, basically pi composed with the inverse of this object, formally speaking. And that's because really this is the signum. What you're doing here is the signum. And that will now be in the functional calculus of this operator, because the signum function is a bounded holomorphic function. So the signum operator is now well defined. And basically square root of pi will just be this object. So it turns out, because this is bounded, it turns out that now the domain of now again I'm running a bit ahead of my own thoughts. So once you have this, you can compare. So this allows you, and it's equivalent to compare, to make the statement that the domain of pi is actually this allows you to prove that a function of the form f0, so in this two-dimensional setting, sits in the domain of pi. The domain of pi is basically this is basically comparable to the square root of this. This is what I was looking for. The boundedness of the Hilbert transform gives you that the domain of pi is the domain of the square root of pi squared. Right? So the difference here is just the signum of pi, which is now bounded in this calculus. But now if you write it out, so take the square root of pi. It's diagonal, so you put a square root here, put a square root here. And now if you test this, test this on functions of the form f0, then you see that in order to be in the domain of pi, you must be in the domain of dh. And in order to be in the domain of the square root of pi squared, you must be in the domain of L. And that gives you the domain equivalence, and if you think a little deeper about the boundedness of this calculus, it gives you the homogeneous estimates as well. By the way, you can also test on 0f, and you get a second equivalence that's not stated here, but it adds to the list. And then finally, how do you prove that this has a bounded H-infinity calculus? The only thing that you need to check, so this is a general result, provided you have these R-boundedness estimates. And the R-boundedness translates into the resolvent. And if you compute the resolvent of this object, you see that what you need is gradient estimates. So you, by working out the resolvent of this operator, you find expressions like domain 1 plus t squared L inverse. And they need to be LP bounded. So the whole thing then finally boils down to proving gradient estimates for the resolvent, or you could also write the semigroup PT. And this is then actually the hard part of the analysis. And so here you use Littlewood-Paley-Stein inequalities, and a lot of harmonic analysis. Let me just cut it short to get these results. And you need to make the distinction between this case and this case, and actually this turns out to be the hard part. So now finally some historical remarks. To get Littlewood-Paley estimates, Littlewood-Paley-Stein estimates for the case P below 2, that's in the paper by Chainovska and Michalik, who were able then in the symmetric case, so the non-symmetric case, because of the B, if B were not there, we would be in the symmetric case, and things would be much easier because you can use duality arguments. And so Chainovska and Michalik were able to use the Littlewood-Paley-Stein inequalities for this part of the range of P, plus duality arguments to get the full result. So in the symmetric case, this result is due to them. I should also mention that in the finite dimensional case, where the bounded space E is finite dimensional along with H under some non-degeneracy conditions, this was also known. Well, this part will then sit automatically in there, so you just get a second Sobolev space. But the proof there really relies on sum of operator methods, which in the infinite dimensional case would give you infinite sums of operators, and the methods break down. So neither the Choinovska-Michalik analysis nor the finite dimensional case is of any help here. So we really have profoundly new ideas to tackle this via harmonic analysis and functional calculus. Okay, so let me stop here.
Thank you. So, thank you very much, and maybe we have just time for one question, and we move to the coffee room.
Does the invariant measure correspond to a stationary solution?
Yeah, you can prove
So
that
what is the solution?
in this very simple setting. That's
You
also.
could write it down more or less, eh?
Yeah. Okay, I have to dig in my memory, but you do something like.
You could do it, isn't it? Don't say
Yes.
You let
If you run the time backward.
Yeah, I think you extend the Brownian motion to
Yeah,
negative
backward.
time route and
Exactly.
integrate that. Yeah.
So
So where does that lie then? That integral? Is it in 8?
That would be in E.
Typically, where would it
Because
lie?
if these measures live on E, that means they are the distribution of E-valued random variables. So a stationary distribution should be a random variable on your probability space with values in the bounding space E.
In the Banach space,
Yeah.
Is that like, it should be Gaussian, huh?
Yeah.
Yeah,
Yeah.
Gaussian distribution.
So you're really talking about Gaussian measures?
Yeah, this is all Gaussian.
Okay, then do you have a absolute continuity of the solution with respect to this invariant measure?
Under your condition.
Under your conditions? Because that would be very interesting if you can get.
Yes, you can show that, but this is. I have some results in an old paper of mine, and they were generalizations of other people's results that were done in slightly more restrictive settings. You can give conditions for the distribution at time t to be absolutely continuous with respect to the limiting distribution. But really, I forgot what the precise statement is.
And you have
I can give you references.
regularity of the density, because you're talking about Marie-Van calculus. So
I have a JFA paper in I think it was 2000 or perhaps 99. I could be mistaken.
and how regular is the density?
Where these conditions are given.
No, the density, mu with respect to mu.
Yeah. So we have a formula for this
How will
in terms of the Mailer kernel.
It's having a regularity.
So, that's a good question. I don't know. And well, my hope is, of course, that once you have this kind of results,
And you might apply
that should be it. And why should that be it? Because if you look at this from the perspective of Marie-Van calculus, what have we been doing? This is really just the Meyer inequalities. So if you just take the one, so in the case, so how do you get Meyer inequalities back? So in a way, actually, this is a new proof of the Meyer inequalities, if you like. So just take H to be R, take E to be R, and take S of T, or take the minus the generator, take that to be identity. So here you are. If you take this example, you get the Meyer inequality. So the statement of this result just then reduced to the classical Meyer inequalities. Right? So in this sense, it is an infinite dimensional and non-symmetric generalization of the non-symmetric, because we're not assuming that L is self-adjoint. Right? So this is a non-symmetric and infinite dimensional generalization of the Meyer inequalities. Well, and then of course Marie-Van calculus is designed to get exactly what you want, right? So now we have the Meyer inequalities. We should be able to get one step further and get this kind of regularity results for densities. But we haven't done so yet.
Keep you busy.
It keeps you busy, yeah. You guys need a good postdoc for that.
So I have my own, maybe
One question?
not question, but because I said one question, is that it seems maybe interesting to go from your results and from what, for example, Da Prata was talking in the first lecture in the conference, to see what can be done in, say, instead of the whole space, in some other subsets of the space E.
You mean analyze this on bounded domains in the Banach space?
Or Hilbert or...
Yeah, well, actually, related to this question is...
But what I want to say was
yeah.
one question, so it was a comment, so let us finish and we can move upstairs.
Okay, I'll tell you up there.
Okay, yeah.
Yeah.